Has everybody met Skip?
How did you avoid it?
So we're doing an interferometer here. What, we got about a 5 or 6 inch spacing?
160 or 1,200 and something miles. 1,300 miles.
Well, take it away.
So, okay, thank you. Thanks, Tom. I'd like to thank Rich Russell first for switching times with me to give me a little more time because
You can sleep during my break instead of yours.
Pardon me?
You can sleep before lunch, tonight, or dinner before mine.
Yeah, because I do want to get to questions quickly, and so I'm going to try to go through this fast enough so that we'll have time for questions at the end. And I'd like to thank Rich Russell also for being insightful and saying, yes, you should use this telescope to do simultaneous study. I was wondering if we could do that. This is about a year ago, right, when we were talking about it. When you were here a year ago.
We did it here first tonight here,
Yeah, we talked about it here at the meeting when I was talking about the SETI that I was doing on the GBT. And that I'd given a bunch of talks on, and we've heard all of that. That was 40-year Donny. So incidentally, Rich talked about 40-year Donny, but this is not, turns out 40-year Donny was in the wrong place for these simultaneous observations that we were doing based on sleep time, other things. And we ended up looking in another part of the sky primarily. We do have a lot of 40-year Donny data, but this is about another pointing direction that's very unusual. And we're seeing some kind of really weird process, having a ton of fun with this system. Okay, so basically what we have is we have two telescopes far apart, 60 foot, 40 foot. They're GPS synchronized with clocks. I'll go through the detailed block diagram a little bit. I won't go through the details, but we're using GPS satellites to synchronize time and frequency. The time sync at each site is within about 9 nanoseconds, and it's disciplined by the GPS signal. The frequency drifts about plus or minus a hertz or two, depending on where the geometry of the satellites are at the particular moment that the two oven-controlled oscillators of the two sites are locked up. We have an almost identical digital back end, which everybody's been down at the 40 foot has seen the digital back end under the table there. That digital back end I've put at Haswell, almost identical one to that. And it runs independently. We started up over there, we started up over here, and we talk over landmines. I'll go a little more detail. And what we're looking for is SETI, basically, with an RFI filter of 1,300 miles. The idea is that if somebody is transmitting on a narrow bandwidth, sparsely filled spectrum, get into that in a minute, and you bring a pulse down to Earth, and you can figure out a way to get the same electromagnetic field across 1,300 miles. And it arrives at both sites, and I look for a quarter second at each site synchronized. And the idea is if something falls in that 1 to 3 hertz, the resolution of the FFT is 3.73 hertz. If it falls in both of them at the same time, on the same frequency, then there's something unusual that might be happening at each site.
Not local interference.
That's right, after correcting for Doppler shift. But by the way, if I don't make anything clear, please just ask, because it might go quicker that way. Okay, so I'm going to talk about how the system works, what we do, how the Doppler works. Search strategies. So this is an idea which is just, there's so many ways to look for SETI. No one knows how the signals are going to get discovered. So this is just one method, and we'll just, we're just seeing what it does. How does the system work? How it's put together? And then I'm going to get to observations and measurement results, which I'm trying to get to pretty quickly. What we want to do in the future. What is our next step? So the way the system works is you got the telescope over here in Haswell. This is the Green Bank telescope. I'm sorry, not the Green Bank telescope, but 40 foot. And this is like if we were way above the equator, beyond the Clark Belt, looking at rays that are coming in from underneath us in parallel. So we've got the parallax, but these two rays are parallel to each other. They arrive at the two telescopes, and they get independently captured. And we do FFTs on 13 million channels over 45 megahertz of spectrum. And it's happening synchronized, frequency and time, at each one of the two sites. Now it turns out that depending on the pointing of the actual signal relative to the beams, the center of the beams and the geographic location of the antennas, the Doppler shift is going to be a little bit different. Okay. Now the beams, this is a 0.8 degree beam width, this is a 1 degree beam width. They cross over about a third of the distance to the moon. Okay, so there's an RFI filter automatically built into the antennas, which gives us differentiation of things that are anything closer than a third of the distance to the moon is going to be rejected due to signal level issues. Okay. Now, of course, you can always have high power RFI, which can leak in on side lobes and all those sorts of things. Okay, the second differentiation here is the Doppler itself. And it turns out that Doppler varies with frequency. It's about 677 hertz at 1420 megahertz due to the fact that Haswell is moving up from Haswell as we're going horizontal, because we're looking straight south, so we have 0 Doppler. So it turns out that's the time that varies with frequency, but it also varies across the beam itself, right? So it turns out if you're within the beam, but there's still parallel rays, you get about 1.2 hertz of delta, okay, plus and minus a half degree, all right? But an interesting thing happens if one of the beams is center of beam and the other one moves across the beam. Turns out if the rays are not parallel, you can get an offset of 15 hertz Doppler. It means that the two are not correcting each other. It has to do with the way the sine waves line up for the two sites. So that 15 hertz is useful because it's about 4 bins. That means if you want to say, okay, well, where does these two rays now cross over, not at the center of the beams, but are not exactly at the center of the beams, but maybe slightly off. And it turns out that line where they cross over, where there's 1 bin of offset out there, is about 720,000 miles. So that means that for Doppler differences on the two sites, within 1 bin, we've got an RFI filter that's 720,000 miles, 3 times, distance to the moon, 4, so roughly. So that becomes the RFI filter that really is important to say we're trying to reject as much as possible that's nearby. Okay. So this is the Glischner telescope in Colorado. I think that's you, Rich, right there.
No?
Right there. I'm pretty sure that's you. And stand to work on it. We put RF fiber in there this summer. I've traveled there 3 times since we started. It's a very remote place. It's one of the best RFI sites that I've ever seen. It's unbelievable. This is the main road to it. There's the dish. It's actually in a Rich told me that it's a meteor crater. It's an ancient meteor crater. It goes around like this. If you're down there and you look around and you can see the horizon, and you can't see the town of Haswell, this is coming out of the town of Haswell. You go down, just slope a little bit, and then you end up going out to the dish over here.
How far to town from the dish?
It's about 5 miles. But it turns out I've used my handheld, my Yaesu handheld, 2 meters, to talk to Paul Birdie with his 50-watt mobile in his car, and I can get my handheld to work out to here. But as soon as I go over that edge and go into the flat part of Haswell, you can't see the houses. It's over the horizon.
Was that?
My handheld dies.
Was that location selected intentionally?
It's a good question. Yeah.
Is your expert on the system?
So if I get on my 50-watt mobile in my car, then I can talk to Paul through it. But that's what it takes. Handhelds don't work at 5 miles. Handheld to mobile. Gary Argonaut is a member of DSCS. He flew 172 over the site. This is what it looks like, pretty much all directions. It's pretty amazing. A couple other pictures here. Such a fun place. This is if you go the other side. So Haswell is like over there. I think that's the grain elevator maybe for Haswell there, or maybe it's, you can't even see it really. There's a grain elevator for Haswell. That's the dish right there. This is the road. I zoomed in on the Canon and had a lot of pixels. Zoomed in on that section. I think that's the NSA building. Am I right, Rich?
Yeah, I'm gonna say building, that's a different story.
This is a black nondescript building in the middle of the field that doesn't make any sense to me.
With 3-phase power going into it.
With 3-phase power going into it. And it has some tractors inside, I heard.
Sure.
That are props.
I'm sure there.
Yeah. It's what's under the tractors.
Down the
We
road.
don't know what's going on there.
We win our big 60-foot dish at it all the time.
I got my NSA shirt, so I'm gonna wear, I'll bring it with me every time I go to Haswell. Okay, so, the 40K everybody knows about. So we put the computer underneath the table here, covered up with the Rfi foam. And I hook up to channel A from here. This synthesizer gets locked to the 10 megahertz coming out of here. The GPS antennas go outside and the GPS antennas sit over here. I put them over in this corner to minimize the potential for RFI to the GBT. And also I built up a special Rfi filter just to be sure, to make sure that there wasn't anything out of the GPS band, and I put that on one of them. And when I was here for the various tests we've done up until this time when I brought both of them. Okay, so what are we trying to accomplish here with this SETI thing? So the idea is that, and it's, you know, this is just one of many, is that we're all communication engineers, okay, and that's physics, you know, that we can't do anything about Shannon's law. So if somebody knows that we are communication engineers trying to receive their signals, and we know Shannon's law, they know Shannon's law, and assuming that it is, in fact, there's no other solution to the problem except follow certain laws about how to communicate, then it turns out using physics, you come to the conclusion that for the least energy per bit to transmit, you want to put signals in the narrowest possible bandwidth, okay? And you want to fill this, but you want to use the maximum possible bandwidth overall to get the highest capacity. That's how Shannon's law works. So to get the minimum energy per bit, it means that you're going to have narrowband pulses, but you're going to have sparsely filled wide spectrum, okay? And this has become sort of one of the approaches that's thought about in terms of what a SETI strategy might be, okay? And that if you have to pack a lot of power into a spectrum, you can get very high capacity, but you have to pay a penalty of high energy per bit that you transmit. And that's the basis of Shannon's law. The other issue is detectability. Is you got to say, okay, now let's spread the spectrum with these sparsely filled tones over a wide bandwidth of frequencies, but if we do that, it looks like noise. What do we do about it? So the idea is to come up with detectability functions so that it's still possible to find out if these signals are not noise, other than just power level, right? Threshold. So the idea is to first get a threshold. The pulse exceeds 12 dB signal-to-noise ratio. So the software measures the noise in 1 kilohertz bands across the 48 megahertz. So it's okay if it's unflat, because each one of the bands is a separate noise measurement. When the signal appears in that bin, within that 1 kilohertz, there's about 256 of them, the 12 dB threshold has to be met for that tone. If the 12 dB threshold is met, which happens about 17 times a second, then we got to say, is there anything else interesting about these pulses? Well, yes. If it turns out that two of them show up really close together, there's something strange going on. Okay? That doesn't normally happen. They're normally separated about 2.5 megahertz, depending on RFI and depending on the other tones that might be present in the system, and that shouldn't produce close tones. So close tones, when we have noise, are not supposed to happen. I'll get to that and I'll explain that in a little more detail. The idea is to open the squelch of the radio. Okay, so this is a communications thing. We want to open the squelch first before we try to look for what might be information. Then after we open squelch, we look for what might be information containing tones, and then that can start to confirm, oh, there might be something there. Okay, so how do we encode information with one tone? That's a pretty big problem. And I mean, I'm kind of lazy. I would like the information to be present in the 1/4 second sample that they gave me. But if they give me only one tone, and now I have to search time for what might be information, I don't know what to do with it. I've got to do all kinds of additional thinking. So why not send the information, try to do it at least, in the same 1/4 second? The second tone doesn't help me much either, but a third tone helps me a lot, because if the ratio of the spacing here to the spacing here is something that is shared between us and the transmitter, like pi, or E, or 365. I've been talking about that for years, other talks here. Then suddenly, in 1/4 second, they can unscorch the radio and provide useful information that says, this is kind of not like human communication systems that we know about. So it's unlikely to be RFI, because it seems to contain some information. And then the question is whether it gets repeated again. So it turns out that detectability is key to getting the squelch to open for a signal that may be extraterrestrial. And I mentioned the 2.5 megahertz approximately. The idea is to take these and occasionally, maybe not all the time, but occasionally put the tones close together enough that they're very rare to occur in noise. So this is a Poisson process. So this is a chunk of the spectrum. This has 17 a second. They cross the threshold. Okay, and it happens in chunks. It's not a full 100% duty cycle system. So but averaged over time, 17 pulses a second. Of those pulses across the 45 megahertz, there's a median delta F. It's around 2.5 megahertz. Okay, so you can take a formula. This is a Poisson process. And it turns out a Poisson process has an exponential distribution on the spacing between the events. So you can calculate that, and this turns out to be the formula for an approximation. But when that delta F over, this is the 50% median spacing, roughly 2.5 megahertz, depending on RFI. You take e to the minus ln 2 times the delta F that you measure on the FFT in that 1/4 second interval. Divide that out, and this is the likelihood that this could occur for every one of the transitions. So every time you see a pulse, you can calculate the likelihood that the next one is going to be close to the one you just saw. Now, depending on how many of these things you look at, you got to multiply that number times the likelihood. That tells you whether or not there's anything meaningful in there in terms of statistics. If you know from here that this is the only one you care about, if for some reason this pulse is the only one we care about, and then we calculate, we measure rather delta F that's ridiculously small and has a ridiculously low likelihood, we don't have to multiply by anything. We just know that it's an unlikely event, at least at that point. Which leads to the issue that if you can identify one pulse in either of the receivers and say, that's very significant, then you only have to multiply by 1, and which means a close tone can suddenly have a very low likelihood and unsquelch the radio. Turns out, if you can get this pulse to be the same pulse at 2 very distant locations, it happens roughly about once a day due to noise. If once a day you can calculate the likelihood of close tones, then you know that something kind of unusual and very rare is occurring. Okay, and that's the beauty of having the second sight, is that we can take this one tone and have a second close tone. And if that second close tone is close to the tone that's simultaneous, we only have to multiply by 1. If it happens somewhere in the range of the same 1/4 second, we have to multiply by about 5, because we get 17 pulses a second. So it all becomes a way of ruling out noise. We haven't ruled out RFI yet. So this is what a typical output looks like. So I call one spacing the numerator, the second spacing the denominator. So everything gets split up into triplets, because that's the fundamental, at least I think, the fundamental requirement to communicate information. The immediately prior tone in frequency, going down in frequency, that spacing between the present tone I call the numerator, and the one to the left of that I call the denominator. So numerators and denominators are constantly overlapping each other. Okay? So you plot them against each other, this is what you see. You see a giant collection around 2.5 megahertz. And then when the tone spacings get small, you start to see much more rare. This is an exponential distribution going down to 0. These are due to starting and stopping pulses that occur at the edge, which cause the value 1 to appear occasionally. Actually, one of them is sometimes due to RFI, the other one is due to the way the starting system works. The idea is to look down here, look for close tones. So the system is set up, I mentioned, I'll just go over this really quickly. It has the GPS receivers at both sites. They're almost identical. I just truncated the RF description on here. We installed the RF over fiber in March this year. Okay, so this is an interesting thing. How do we make sure we timestamp the stuff correctly, all right? And over the years, as I built stuff, I always get nervous when I try to timestamp something and then, based on what the software is doing, predict that, oh yes, that is the correct time. Because computers go off and do their own things for a while. So it's really hard to encode time into computers themselves. It's much better to do it in the hardware itself. So this box produces an IRIG time. This stands for International Rocketry Instrumentation Group. And they developed a way to encode time in a BCD kind of format that is ones and zeros. That gets sampled on the B channel of the scope with the same clock and the same trigger as the data itself that's coming in from the antenna. So what that means is that the data that's fed over the USB 3.0, 5 gigabits per second, is interleaved A and B channels with the time domain data of the telescope. All right? So then when I take the code and I write the code to extract that and I demodulate those pulses from the IRIG, I can be sure that that particular FFT and time sample is being performed at that particular quarter second. It was on that. Now there's also a 4-second time trigger that gets developed in here, which is synchronized with the other site. So we make sure we start our 4 seconds on the correct 4-second interval. And we prove that they're correct. Well, one thing is we set them with a script that I write, and it's the same script at both ends, so they start with the same bash script to guarantee that I send a serial message to each one of them. We do it at different times, but we make sure we do it on the 4-second. The 0 of every minute, okay, we make sure they're synchronized. And then we talk over the phone, and we look at our modified Julian date postings at each site, and we verify the modified Julian dates match up to all the digits. So that's like a confirmation. I get nervous about almost everything, as you can probably imagine. Things don't work always. Okay, so system pointing validation. So the first time we got a system pointing validation where we tried to get both antennas lined up with each other, this is what we saw. Now this was when we had coax at Haswell, and the wind was blowing, and so this is NRO 5690, which happens to be about a third of a beam width from the -7.6 declination arc that we transit. So we don't steer, we point south and we point the other dish offset, Haswell dish offset, so that they line up at the -7.6 declination arc in parallel arrays. So this was our first confirmation that we had both dishes on the same pointing direction for NRA. That's about a 90 Jansky object. And this was after we put in the RF over fiber, and there's still some glitches which we're not sure about, but it's a much better agreement that we're pointing, and also that the noise floor is about equal on both sides. Okay, so this data is taken by in the software. Each site calculates the continuum for the full 48 megahertz over 1 second. Okay, so this is an integrated 1 second, 48 megahertz continuum measurement at each site, and then posted to the file along with each one of the pulses. So that gets posted to the file together with the 17 a second of the pulses that are seen at each site. So I'm going to just talk about this very quick. This is a side note, but we don't have to assume that all the signals at one site are present at the other site. And the reason is, this is what we're doing today, even with 4G cell phones, is you are getting information to your phone, 4G, 700 megahertz, for example, from the tower, from 2 separate antennas with signals that are on top of each other. They're the same frequency. They're transmitted from the site and coded in a way, when your phone has 2 antennas on it, it receives 2 signals, and 1,000 times a second it calculates the scattering from the site, and you're able to get twice the capacity to your phone because it is separating out the 2 signals that were coded on the 2 antennas. So your data rate actually doubles. It means that if you can put multiple antennas of your receiver, multiple antennas of your transmitter, you can double the capacity in theory. It turns out in 4G it goes average about 1.5 because there isn't always the necessary scattering. But in theory, it can be as high as 2 if they're able to invert the matrices and get the 2 channels to be well orthogonal at high signal to noise ratio. So it turns out someone doesn't have to have a single source. They could have something spread out over multiple astronomical units. So I did a calculation here, and I found out that on Earth you could put about 100 beam widths across the planet with something that's 2 astronomical units at 16.3 light years away. Okay? Well, why would they do this? Because with the same antenna hardware, they could transmit 100 times the information to the planet. So when you look at this thing and you say, well, wait a minute, we're only getting 17 a second, and occasionally, and there doesn't seem to be much data there. But you could multiply what you're seeing on any one antenna times 10,000 if you had a full 2D array on Earth that they could build out there. Now, they do need the energy per bit. So every bit that gets transmitted, they do have to supply the energy, which means at the transmitting system of antennas, they do have to have the energy available, solar or some other way, to add that additional capacity. But they don't need the infrastructure of the antennas. They just sum the signal in and transmit it out. Okay, so the reason I bring this up is that we shouldn't assume necessarily that every pulse we see at one site is going to show up at the other site. However, if we don't assume that, we have a detectability problem. All right? Because we can say, well, if the signals are not at both sites, how can we know that they're very far away and intentionally transmitted? So the idea, it's just a crazy idea, but, it's one thought. Well, why not, they know that. They know that we're going to also say, well, we're trying to differentiate between real stuff and noise. Well, why don't you every now and then, to use up 1% of your capacity, and send 1% of your intentional pulses on the same frequency at the same time to the entire planet, okay? And it turns out, if we look at the statistics of what happens when we receive something, we will immediately say at both sites, hey, I only saw one of those pulses. The rest of them are very rare, and they seem to be occurring, but none of the other ones were on the same frequency at the same time. So it turns out, almost immediately, you can learn that intentionally, they're transmitting different signals across the planet, just with a simple detection, without any decoding. Okay, so this is the observations, and I have about 20 minutes, I think, almost. I'll go through these pretty quick. Okay, so we've done a total of about 1.5 days. November 25th, April 11th, and I've been doing standalone here down for the last 3 more, June 7th, 8th, and 9th. But I'll just, I'll try to get through this quick. In the 1.5 days, we should have seen about 1.5 simultaneous 1 hertz to 2 hertz to 3 hertz, about 1 bin. It's a root mean square of the bins and the bin spacings, and also the plus and minus 2 hertz if the GPS constellations were off a little bit. So we saw this thing right here. This was the first one we saw. This calculated out to be a 1 hertz offset mathematically, based on the calculations, even though we can't resolve that to better than 3.7. This is what we see. This is after post-processing the 2 files. So I bring them together, and then I search one. I take for every tone I see on one file, I search the other file. Do a binary search, get the time first, find the time, and then look for the frequency. See if it's the same opposed to it. And this is what we typically see, and this is what we would expect. You'd see maybe 1. Okay, so there's 1. So this one, in November 25th, was really interesting because it turned out this is the simultaneous pulse. The Green Bank system had a 13.92 dB SNR, 1.92 dB. That's an exponential distribution, going above 12 dB. You shouldn't see that very often. It's pretty rare. I'll go into the number. 80 kilohertz off from this one was another tone. Should have been 2.5 megahertz. This one had a 73 kilohertz offset. Should have been 2.5 megahertz. So something strange about these 4 tones. These were the next tones over that occurred in that quarter second. So this is all happening at the exact same time, the same quarter second. And we're getting some unusual close spacings and a high SNR over here. Okay. This is November 25th. So we can calculate the probability of the 13.92, the likelihood, and this is ranked the 950th highest of 53,000 pulses. Okay, so this tells you the likelihood of seeing a 13.92 dB randomly. Okay. The nice thing about it, it was only on 1 pulse, the simultaneous pulse. So we don't have to multiply by a big number. We know that the likelihood, and it's roughly about 0.017. About 1 out of 50 times, you're going to see an SNR that I just randomly picked. Okay, so we just do a likelihood analysis on this because we're trying to build a squelch function. We use SNR for our squelch, and we use the 2 tones offset, and we do a calculation of that. We have to take into account, whether there might be 2 of them, because it could have been either one of them. Could have been 13.92 dB, so we multiply by that number, and we come out with 31 ppm. So when that pulse occurred, if it happened a million times, we should have seen 31 events that look like this. Now, if somebody can imagine another squelch function, because this one might be driven by confirmation bias, we got to multiply by 2. Some other, like maybe it wouldn't be the numerators, it would be the 2 denominators, all right? We've got to multiply by 2. And sometimes you have to keep multiplying by as many things as we can think of that might have been a useful squelch function. But this by itself, the next tone, next to the simultaneous pulse, and SNR are natural communication squelch functions. Okay, so that kind of got my attention a lot. Okay. So then we look for, is there anything else happening around the time of that simultaneous event? So this is what it looks like when we look at the whole. This is a 1/9 of the total spectrum, the 45 megahertz, and this is 4 hours. And this is what the file produces. The simultaneous pulse is in here, when it has the close tones. It's in there somewhere. I don't know which one it is, because I didn't want to hold the marker to find it. But then I zoomed in a little bit to 1 megahertz, and it's that red dot right there. Okay, that's the one that's the same. It's 4 hours. Zoom to 1 megahertz range. Okay. And then this shows the beam width of the antenna. So the beam width is here because this is modified Julian day. This is the spectrum now at 1.4 megahertz. And there's the red point right there. That's the Haswell and Greenback simultaneous pulse. Right there. The little red ring. And then we zoom once more. And this is what it looks like close up. So now we're at 120 kilohertz of zoom. And this is still at 17.8 seconds. That red dot is the simultaneous pulse. There's a partner pulse 8 seconds away at 1.6 kilohertz offset next to the simultaneous pulse. It has a likelihood of about 0.01. So we would have to do this 100 times to get a pulse that close. And you can kind of see from these things that, yeah, those two are kind of the close. These two are close, but again, we don't know what these signals are. Some of this stuff could be intentional. It could be RFI. So we don't know what these things are. But in general, if it's noise, the separations kind of follow the math of what we expect to see in terms of separation. So it turns out that the other weird thing is up there, there's a pulse that's 14.39 dB SNR. That turns out to be the 4th highest signal-to-noise ratio in 4,605 pulses that covered 1 megahertz. From 1429 to 1429.99. This was of just that part of the spectrum, okay, this was the highest, the 4th highest in 4,000. Okay, and that happened 16.75 seconds later than the simultaneous pulse. So things are getting a little weird to start seeing a group of things together. So the partner pulse comes up later, and I'll talk about that later, but now we look at the partner pulse itself. These are the 3 tones that are associated with the partner pulse. Remember, it's 8 seconds off that the partner pulse occurs. The partner pulse itself has 3 close tones. All right, that's kind of crazy. You can't see them on the plot because they're a little bit farther than this 120 kilohertz span, but they are there at the same time, and there's 3 of them. It turns out the event rank. So I calculate likelihoods and mathematically, and then I also use the data itself, assume it's noise, to calculate the rank of that particular event in the overall events. And those two, they generally agree pretty close because we've got a lot of pulses to look at. And so they do, and it turns out this happens 7 out of 1,000 times. So 7 out of 1,000 tries, the closest pulse to the simultaneous pulse is going to have a spacing that's as close together of all three tones. But there it was. Okay, so that's kind of crazy. So there's several ways to calculate this. One way to look at it is to say, all right, let's look at the partner pulse and let's look at the simultaneous pulse. These are the 9 frequencies associated with the partner pulse, 1.6 kilohertz off, and 7 of the 9 frequencies, 1, 2, 3, 4, 5, 6, 7, are closely spaced. Okay? And it turns out the probability, the estimate of a likelihood of 3 events like this happening, it's like 3.6 times 10 to the minus 8. There's various ways to calculate this, but we can basically say, well, yeah, because it is rare if it should be 2.5 megahertz and it's 1.6 kilohertz and all these kinds of things. Yeah, so you are going to get a pretty small number when you take a multiple of those things that all seem to be happening at the same time. So this is kind of rare. This seems weird. Okay, so now that was all Green Bank. Now we go to Haswell. This is what Haswell looked like. At the time of the simultaneous pulse, in that quarter second, those pulses, when they popped up, had tones that looked like this. 2 tones spaced close at 1429 megahertz, 2 tones spaced close at 1434 megahertz, 2 tones close spaced at 1441 megahertz. This one has a probability multiplied by 2 because there were 2 tones in between these two. So when you calculate this one using that likelihood function, the Poisson exponential, you got to multiply that by the number that you looked at. Turns out one of these was RFI, so I verified that this one is RFI. But we have to multiply by 2 because we had that one, and then we had this one. So these are the probabilities that this kind of thing could happen at the same time, in the same quarter second, as those tones popped up across, the band, and roughly 15 or so of them. All right, so what happened on April 11th? It turned out between November, we had a lot of equipment issues and other things that we had to deal with. And so we weren't able to get really back to continuous, simultaneous running until April 10th and April 11th. This is the April 10th simultaneous data, similar plot that I was showing you. Frequency offset, Haswell to Green Bank, and modified Julian date. This is the April 10th, and then we have sleep and stuff. I don't run things at the 40 foot unless I'm there. So that's, just my own, I brought sleeping bags, but I haven't been using sleeping bags down there yet. This is the April 11th data, and there was this pulse here. There was this one, which is about 1.5 hertz. And there was this one at 4.3 hertz. Now, I looked at this one a bunch, and I can't see anything unusual about it, okay? At either site, Haswell data, Green Bank data, it looks like noise. Okay? I can't see like a plethora of little pulses along with it and little partner pulses and other things. So this might be noise, I don't know. This 4.3 hertz offset, it turns out, through all these pointing directions that were going across the sky, turns out it's 0.6 degrees away from the one I showed you previously on November 25th on the sky. Okay? So it was within the beam width. And that kind of got my attention. That was kind of weird. But it should be after scanning the sky, you'd see the simultaneous pulse happens to be 0.6 degrees off from where we saw it in November, celestially. Now, I'm just going to go over this really quick, but I try to decode the numerator and the denominator in these things and say, if somebody wants to get my attention, why don't you give me some really unusual numerators and denominators? And when I calculate the ratio of those two numbers, maybe I'll see something weird. Well, most of you have seen these presentations for years, and you're probably getting tired of them. Well, I'm tired of them too. That's why I don't talk about this very much. But I see weird ratios. You see this ratio here? It has no 1, 2, and 8 digits in it. So if I take the bin spacings and I divide them out, there's no 1, 2, and 8 digits. There's the probability of that. It's about 2 in 1,000 tries that you're going to just take a random ratio of 2 integers, and it's going to not have 1, 2, and 8 digits in it. This is the Haswell ratio, and this is the Green Bank ratio. This is the simultaneous 4.3 hertz pulse at both sites, and this is the calculation of the ratio for the 2 sites. Okay, the tones were different at the 2 sites, except for the simultaneous pulse. That simultaneous one was on the same frequency at the same time, but the other 2 were different at each site. this thing has no 4 and 5 digits in it. It's a weird number, okay? And it turns out that probability is about 2 in 100 tries. Now, the reason I put this slide up is just because this is the kind of, I've been seeing this stuff way too often to ignore it. And when I see it on a simultaneous pulse, I just report it. This is my observation. It may be totally all up here, okay? It just happens to occur, but it seems rare. And it's hard to, it's also hard, extremely difficult to imagine that the actual integers, are being transmitted. Okay, so let me go back through these pretty quickly. Now here's what happened at Haswell on the second continuous pulse. This is the 0 time, right here, of the continuous pulse. There was a 29.337 spacing on Haswell. 4 seconds later, there was a spacing here of 59.3. Here, 15.7, there was one over here at 63, and then there was a 9 kilohertz spacing right here. There's actually 2 points inside that circle. This all happened within 20 seconds after the simultaneous pulse occurred. There was also a 14.145 right there. So these are the likelihoods, 0.008, 0.016, 0.018, etc. The likelihood that you would see it on any one particular one of these tones that might appear, that are appearing in the plot. Okay. Now, when we go to Green Bank from Haswell, so that was Haswell, we come back to the Green Bank data, and we look at this is the simultaneous pulse, the red one right there. There was a partner pulse at Green Bank. It was offset by 53 bins. That's 160 hertz or so, right? 53 times 3.7, almost 200 hertz, okay? Why would there be a 200 hertz tone at Green Bank that was that close when it should have been 2.5 megahertz to the simultaneous pulse at the two sites? Okay? The estimated probability of that's going to happen about 3 times every 10,000 tries. So every 10,000 simultaneous pulses, we should see a 53. And now we look at over time, and this shows that we don't have a 100% duty cycle. Each of these is the quarter-second intervals, and then each of these is a second. So here's what happens at the simultaneous tone. We see this, and it turns out in less than 4 seconds later, in the next group of samples here, there's a 102 bin tone offset at 1433 megahertz. Okay, likelihood about 0.07 on that. These two, turns out, those two offsets, if you say, what is the probability we're going to get 2 close offsets over the full time record that we have, given that this is a pretty small duration of time, we can do a binomial on that. We say, we're going to try 22 times, and we're going to see it twice, with the probability is the ratio of the 4 hours that it could have occurred over the time that it actually occurred. And that turns out to be 1.5 times 10 minus 5. So that should have happened. This sort of 2 tones close together, twice, really close together, should happen like 2 in 100,000 tries, roughly. Okay, so June 7th to June 9th, I don't really have time. I don't want to get to questions. So I'm just gonna say that I just went down there, did standalone, and I saw like a whole bunch of pulses. This is pointing in the same direction. So this is captured within the same direction. The thing that's weird is that when these tones occurred at the same time, it turned out the frequency, there was a frequency at the same time, which was the same as the simultaneous pulse from April 11th within 1 kilohertz. So that seemed kind of crazy that happened. And then I got a more plethora of tones together. The product of these likelihoods is like 10 to the minus 9. This one was off by 22 kilohertz. And this was 3/4 of a second before. This occurred 3/4 of a second before the other one. Okay, so really that likelihood is calculated only for this event. You have to multiply by about 4 or maybe 10 to account for the fact that, well, no, we're not looking now, we're looking 3/4 of a second off. So that means we got 4 samples that we could have used in our likelihood calculation. So the function has another factor in it, but it's still in the order of 10 to the minus 8 or so. And this was the June 9th, which had some ridiculous 127 bin offset. Again, this is within the beam of that same pointing direction. Okay, so because I'm running out of time, this is what the sky looks like here. This is the April 11th. This is the June 7th. These are the 5 events in the days that I'm presented. And this shows that they occurred over a period of 227 right ascension seconds. And the beam width is 266 right ascension seconds. So all of these things that I described in the previous thing all fall within the beam width for this pointing direction at minus 7.6 declination. All right, so this is what the sky looked like. That circle is 1.5 degrees. The Milky Way was over here. This is the pointing direction. Hipparchus 112774 is a little bit outside the beam width. It's about a degree off the beam width, and it's the closest star in that area. There's an M class that's 60 light years. That's closer. It's in the beam width, but it's up a little bit more on declination, a little bit off. They're both a little bit off. So okay. Conclusion. So I love observations. It's conclusions I have a problem with. I don't like to make them, okay? And I'm not ready to make them yet, because I consider this as kind of an engineering issue. You know, there's too many unknowns and too many anomalies and weird things at this point to make conclusions, plus we have a lot more observing we're going to be doing. So all I'm saying is we need follow-up. Now, what are we going to do? Originally, I wanted to have these two sites communicate. Okay. Two sites, we're no longer going to make them communicate. We're not going to do that. The thing we're going to do is put up a third site. Okay. And these are other minor things we're going to do, but the best thing to do right now is put up a third continuously operating site. Okay. Thank you. Thanks, everybody. Okay. Any questions about this weirdness? Pardon me?
We're too confused to ask questions.
Well, you know, just in a nutshell, it's going boom, and then it's going blah, 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 boom, blah, blah, blah. That's what it looks like. A lot of close tones that are improbable, that appear to be modulated signals, at the time, or within seconds of the time, of the simultaneous pulses of the two locations, in the same pointing direction of the sky. And that's just it in a nutshell, right? With all the various slides, the four occurrences, the two occurrences with the two Haswell and Green Bay stuff.
So it certainly seems like I have trouble following the probabilities and everything.
Mm-hmm.
One thing you could do is sort of attest that it's not something about the data processing is really just swap the times, like just pick a random, like move everything over by an hour in one data stream and then do the same thing and make sure that you don't see these events when you know you shouldn't see them.
I should rerun the post-processing with the wrong Doppler. That's a great idea.
Some different way of just
that
way
is,
you could
yeah,
use
or
sort of
time and Doppler. That's a great idea. I should rerun my post-processing software with Doppler and time offset, like dithered around various places. That's a great idea.
So you have established these strange coincidences are more likely than they should be statistically. Is that?
Well, that's where these 10 to the
right?
minus 6s and 10 to the minus 8s and 10 to the minus 5s are going on each one of these events as they occur. When these numbers, when you start to see a lot of close tones at the time of an event, which shouldn't happen once, it should be once a day. And then we say, oh, well, we've also got all these close things happening at the same time as that one-a-day event. Well, then it attracts attention. You know, I worked at HP for 27 years. I've told people this story, but I built test equipment, and we gave it to scientists to use for their instrumentation, for their measurements of their experiments. And if this was noise but not the sky, and it did this, I couldn't ship it. I couldn't ship that product to the customer, because the customer would see these weird improbable anomalies and say their equipment's broken. So this is, at this point, it's an engineering problem. Okay? This is a problem to find out what in the engineering of this simultaneous system can cause these kinds of probabilities. Where is the math that explains these events?
Or is there a natural phenomena that could cause these events, which is
Yeah.
beyond our comprehension at this point?
Yeah. So applying noise is the other thing, and I've been applying noise to the system. That's really important, and I do that periodically. I just disconnect everything except noise, and then find out what happens with noise. Because
So
you
just take the random front-end noise of the receiver without hooking it to the antenna?
Yeah.
You don't see any of these
That's exactly what I
correlations
do.
at all?
And to some extent, it happens anyway because we're looking at a dark sky, you know, or what we think is, you know, nothing's out there. So the events themselves, I mean, for example, if I was seeing like 10 or 12 simultaneous pulses, and I calculated one a day and I'm seeing 10 or 12 at the two sites, I go, okay, we can't ship this. We can't ship this product. It needs to be worked on. Figure out what's causing that. The numbers do seem to be about right. Yeah, but
Is it the same photon that is being received in both telescopes traveling from the source?
so when somebody told me not to put photons on my slide. I love photons. But because H nu over KT at 1.4 gigahertz is so small, for every one of those, like even at 3 dB noise, we're at thousands of photons, right? So that 12 dB SNR is probably 20 or 30,000, because it crosses over at 1 Kelvin at about 12 or 19 gigahertz, somewhere in there, the H nu over KT line. So you only can count photons themselves when you get up to like 20 to 30 gigahertz, and then temperatures down in the vicinity of 10 Kelvin. And then in a bandwidth's on the order of 1 hertz, and then H nu over KT starts to look like basically individual photons. But this is hundreds of thousands of photons.
Okay, so
But I just said photons just because it's light particle. You know,
But
on the slide.
physically, is it possible that the same photon is presented to both telescopes at the same
That
time?
depends on the definition of a photon.
Well,
Does a photon exist
everything is
before?
photons. I mean,
Does
space-
it exist in the first place, or
This
is
is
it
a
a
huge
mathematical
question about
construct?
wave particle dualities. I don't know. We could talk about this up in the Drake Lounge.
Okay, so it's the same way.
I think I missed that. Where the both were pointing at?
They were both pointing at that Marcus 112774, slightly off when the events occurred. But they were transit, so they're minus 7.6 declination arc all the way around the sky celestial. And that's what all that data is. So the reason we were doing minus 7.6 is because I've been doing SETI, as you know, for a long time. Since I was a kid, actually, but for the last 4 or 7 years, I've been doing it on my farm with a 5.4 meter and 5.8 meter, and I've been doing this with it, with the same kind of FFT backends. I've been going like this with it on declination. I always wanted to stay close to the celestial equator because I get a lot of angular differentiation on a small telescope. But I started to see weird things at minus 7.6. So that's what I did, yeah. Okay, thanks.